Hello students. In this video I want to take you through Newton's method. So Newton's method is a technique for finding zeros for a function, or sometimes we call them roots. A lot of times people use the term zeros or roots interchangeably, although I think roots really should correspond to polynomials and zeros should be just functions in general. But people do use them interchangeably, root finding or zero finding. Anyhow, let's assume that the zero of our function is this number r, and that means that if we plug r into the function, we would get 0. And now this is on the continuum of real numbers, so of course this isn't going to apply necessarily in our computations and in our algorithms because of floating points, so we're going to see how close we can get to 0 within a certain tolerance. So keep that in mind. So geometrically, we're looking for where does the function cross this axis here. All right, so let's see, what is this going to look like? We're going to have, let's do a Taylor series expansion. We're going to have f of the root is equal to, okay, now we're going to expand about the root, so, or expand about this iterate x sub k. So if we do that with this Taylor series, we'll have f of x sub k plus, and then write r minus x sub k times f primed plus, and then we have the second order term here. So I'm going to move this around. I'm going to do a little bit of algebra. But first I have to realize that, right, f of r is 0. So I'm just going to make that 0. That's our hope, our dream is to get that to be 0. And everything else will stay the same, except I'm going to call this r minus x sub k quantity squared. I'm going to call that ek squared. This is going to give us a convergence rate. And then I'm going to move, I'm going to solve for r, so I'm going to move everything else over to the left-hand side here, and then divide by f primed of k, and I will get the following result here. Now, we don't know r, so we're going to replace that with the next iterate, x sub k plus 1. And I'm going to replace this quantity here with some number, let's just call it ck. It will depend on the iterates. So you can see now that we have Newton's method here. The next iterate is equal to the previous iterate minus this ratio. And this term should go to 0 as xk converges to r. So, and if it does converge to 0, it's converging to 0 by its square. So that's pretty fast. Think if the difference between the root and x sub k was 10 to the minus 1, that means in the next iterate it'll be 10 to the minus 2. In the following iterate it'll be 10 to the minus 4th because you're squaring it. In the following iterate it'll be 10 to the minus 8th. And then the next iterate it'll be 10 to the minus 16th. So in 5 iterations, this difference between r minus xk should go to 0 in only 5 iterations. So Newton's method should be pretty fast. We call that convergence rate quadratic. What I've boxed in here in green is, in fact, Newton's method. The difference between x sub k plus 1 minus x sub k, we call that the iteration error. And notice that I can replace that iteration error with this ratio. We're going to assume that f primed is not equal to 0. Now, a lot of times in your algorithm, you'll want to put an error trap in for that. I am not going to do so. I just want to get the concept across here. We could call this ratio, let's say eta sub k, you can call it the iteration error, whatever you want. And you could think of Newton's method as the next guess is equal to the previous guess minus a little bit, a little nudge. And that gets you closer to the root. That's Newton's method in a nutshell. All right, in the next video, I'm going to take you through coding up Newton's method.